Good morning, students. Myself, Vaidegi, working as Assistant Professor in Sri Muthukumaran Institute of Technology. Today, the video lecture is from the subject CEC 334 Analog IC Design for 6th semester ECE students. Today, the topic is from the Unit 2, Unit 3 Feedback and Single Stage Operational Amplifiers. In this lecture, we will discuss feedback in amplifiers and important operational amplifier parameters. Feedback is widely used in electronic circuits to improve stability, reduce distortion, and enhance overall performance. We will examine different types of negative feedback, understand the effect of loading in feedback networks, and study key parameters used to evaluate operational amplifiers. First, we see about the introduction. Let us begin with the concept of feedback. Feedback refers to the process of returning a portion of the output signal back to the input of an amplifier. There are two main types of feedback. One is the positive feedback and second one is the negative feedback. In positive feedback, where the feedback signal is in phase with the input signal. In negative feedback, where the feedback signal opposes the input signal. In amplifier design, negative feedback is preferred because it improves stability and reduces unwanted effects. Throughout this lecture, our focus will be on the negative feedback only. First, we see about the negative feedback. Negative feedback occurs where a fraction of the output signal is fed back to the input in opposite phase. The closed loop gain of an amplifier with a negative feedback is given by AF equals A divided by 1 plus A beta, where A is the open loop gain, beta is the feedback factor, and AF is the closed loop gain. Although feedback reduces the overall gain, it offers several advantages. These include stable gain, reduced distortion, increased bandwidth, and lower noise. This trade-off makes negative feedback extremely useful in practical amplifier circuits. Next, we see about the properties of negative feedback. Negative feedback provides several important benefits. First, it improves gain stability. Even if transistor parameters change due to temperature or aging, the amplifier gain remains relatively constant. Second, it reduces distortion by making the amplifier response more linear. Third, it increases bandwidth, allowing the amplifier to operate effectively over a wider range of frequencies. Fourth, it reduces noise and unwanted signals. Finally, it allows designers to modify input and output impedance according to application requirements. Next, we see about the types of negative feedback. Negative feedback circuits are classified based on how the output is sampled and how the feedback signal is mixed with the input. There are four basic types of feedback: voltage series feedback, voltage shunt feedback, current series feedback, current shunt feedback. Each type affects the input and output impedance differently. Selecting the proper feedback topology depends on the desired amplifier characteristics and application. First, we see about the voltage series feedback. Voltage series feedback is also called series shunt feedback. In this configuration, the output voltage is sampled and fed back in series with the input signal. This arrangement increases the input resistance and decreases the output resistance. Because of these characteristics, voltage series feedback is commonly used in voltage amplifiers and non-inverting operational amplifier circuits. It provides good voltage gain stability and excellent overall performance. Next, we see about the other feedback types. Let us briefly compare the remaining feedback configurations. In voltage shunt feedback, both the input and output resistance decrease. In current series feedback, both gain stability and current sensing are achieved with increased input and output resistance. In current shunt feedback, the input resistance decreases while the output resistance increases. Understanding these impedance changes helps engineers choose the appropriate feedback topology for specific applications. Next, we see about the effect of loading in feedback networks. In practical circuits, the feedback network is connected between the amplifier input and output. Because the feedback network draws current, it may load the amplifier stages. Loading can cause reduction in gain, changes in input values, impedance values, variation in the intended feedback factor. As a result, circuit performance may differ from theoretical calculations. To minimize loading effects, engineers often use buffer amplifiers, impedance matching techniques, and high input impedance devices. Next, we see about the operational amplifier. An operational amplifier, commonly called an op-amp, is a high gain differential amplifier. It amplifies the difference between two input signals. The key characteristics of an ideal op-amp are very high voltage gain, very high input impedance, very low output impedance. Because of these properties, op-amps are widely used in amplifiers, filters, oscillators, signal conditioning circuits, and many other electronic applications. Next, we see about the op-amp performance parameters. Several parameters are used to evaluate op-amp performance. The first is open loop gain, which is gain of the op-amp without feedback. The second is input offset voltage, which is the small differential voltage required between the inputs to make the output exactly zero. The third is input bias current, which represents the small current flowing into the input terminals. Another important parameter is the common mode rejection ratio, or CMRR. CMRR indicates how effectively the op-amp rejects signals and are common to both inputs. A higher CMRR means better noise rejection and more accurate amplification. Next, we see about more performance parameters. Let us now discuss additional performance parameters. The slew rate is the maximum rate at which the output voltage can change with time. It determines how quickly an op-amp can respond to rapidly changing input signals. The gain bandwidth product, or GBW, is another important parameter. It states that as gain increases, bandwidth decreases, and their product remains approximately constant. Finally, the power supply rejection ratio, or PSRR, measures the ability of the op-amp to reject fluctuations in supply voltage. A high PSRR ensures that changes in the power supply do not significantly affect the output. Finally, we came to the conclusion of this lecture. Let's summarize this. To summarize, we studied negative feedback and its advantages, including gain stability, reduced distortion, improved bandwidth, and lower noise. We examined the 4 basic feedback topologies and discussed how loading can affect amplifier performance. Finally, we reviewed important operational performance parameters such as open loop gain, input offset voltage, input bias current, CMRR, slew rate, gain bandwidth product, and PSRR. These concepts are fundamental for analyzing and designing reliable analog electronic circuits. Thank you for your attention. Hope you all understood. Thank you.